So the whole aim behind this series of lectures or talks is to take us through paleoclimate reconstructions from a statistical point of view, and hopefully quite slowly. And it's worked mainly based on some of the work that we have done recently, but also it goes back to some of the work that has been done by others. So initially, in the first third of this specific seminar, I'll give an introduction to statistical paleoclimate reconstructions, and then I'll go to the second third to what many of us know as the hockey stick, right? How to reconstruct temperatures of the past, and then eventually to uncertainty quantification. Like when we reconstruct climates of the past, well, how much of confidence can we put on these reconstructions? And that becomes essentially a statistical problem, right? And as you'll see, I'll try and take you through it gently at any point in time. Please just stop me and feel free to ask questions, because it is most probably a new topic for many of us here. So here is a diagram, which is a plot of temperature reconstructions. On the x-axis, we have years in Anno Domini 2000, going all the way back to 800. And these are temperature anomalies, right? Difference from some mean. So these are referred to as temperature reconstructions. So we have temperatures mainly up to about 1850, historical temperature records. Beyond that, it's very scarce. So these are called temperature reconstructions. And this is taken from the Intergovernmental Panel on Climate Change, Assessment Report 4. And these kind of diagrams or pictures have been the poster child of paleoclimate reconstruction. So usually when one refers to paleoclimate reconstructions, you may have seen it in the major news outlets and in scientific publications. This is one of the big poster childs. And this curve is often referred to as the hockey stick. And Michael Mann was...
Actually, it's the one from the AR3, which was referred to as a hockey stick. This doesn't look quite as much as, because it has this fairly broad and variable thing to the left.
Michael, you didn't hear what I was saying. I'm just saying this is from the IPCC AR4, and the concept of a hockey stick was introduced by Michael Mann. Those are two different issues.
There was a picture like this, which was a really big thing in the previous assessment report. This is a milder version of what was done a few years ago.
Yes, what I'm saying is completely different from what you are saying, which is the following. This concept of doing paleoclimate reconstruction has been dubbed in the media as a hockey stick. Yeah. It's not in reference to this particular picture, but this general philosophy. So let's not get stuck in the details or in the semantics. Okay? I'd rather focus on the science. So why do we care about these questions? Some of the most fundamental and expected significance of why we care about this is, well, what do historical temperature measurements, right, tell us about the sensitivity of climate to greenhouse gas emissions? Okay? We want to understand how the Earth responds, and how can they be used to validate climate models, right? So not only looking at the past, can this help us to project in the future and to produce reliable regional forecasts, right? A question that's more dear to me and more important to me is that kind of temperatures that we see now, right, climate, how anomalous are they in a millennial context? Anomalous, how different are they? What we see now, is it really different from what was observed before? Well, we haven't observed much before because we don't have instrumental records from before 1850. And Europe, yes, farther back, but not much farther back, right? So, and what is the link between, right, hurricanes and tropical cyclone intensity and ocean warmings, right? So trying to answer these questions, of course, needs data sets which are reliable, long, and with broad spatial coverage. Now, if I knew what happened from a temperature point of view, or thermometer or temperature records all the way back to, let's say, 500 AD, I wouldn't have to do much. I would be able to say how different we are now. Well, unfortunately, this is not always possible because direct physical measurements of climate fields are limited both temporally and spatially. It means that going back farther in time, right? In terms of actual, the invention of the thermometer, we don't have temperature records, right? And they're also, in terms of spatial coverage, they're very poor. If you go back to the New World and to other regions of both Australia, Asia, well, the spatial coverage is very poor, especially also in the oceans. Vast swaths of the ocean, we don't have data. And even only recently, shipping routes were used to collect to data. So that's a problem. So, and measurement quality also is poor, and availability decreases back in time. And as I said earlier on, instrumental records are only available for the last 150 years, roughly speaking. Of course, there are some places where they are, especially in the UK and some parts of continental Europe, some data goes back, but it's not very reliable. And as I said, large regions of the South Pacific and the Equatorial Pacific, we care about the Equatorial Pacific for various reasons, right? Are afflicted by missing data, measurement errors, and biases because of change in observational practices. Sometimes stations move around, and so there is a break in the record. So there are all kinds of problems that we have, missing values, coverage, both temporally and spatially. So these are some of the challenges. So even more challenging is, well, since we don't have this kind of data, hemispheric temperatures of the past millennium can only be inferred from what I refer to as sensitive geological proxy data. What do I mean by that? What do I mean by proxy data? Well, tree rings, ice cores, sediment cores, right? Speleotherms, and so forth, and corals. Now you may wonder, well, what are these things? Well, I'm saying that these are the Earth's natural thermometers, and they do have carried climate signature. And we may be able to use them to try and understand what climate was, let's say 1,000 years ago. Right? Can we do that? Right? And so there is scope for using paleoclimate proxies to reconstruct climate variables. So if these are, I would say, surrogates for a thermometer, as a tree grows, right, and it reflects temperature and other factors, so does coral growth in the oceans, right? It doesn't only it doesn't only depend on the temperature in the ocean, but it also depends on salinity around it. However, it could be used potentially to try and understand what the temperature was going back in time. But this proxy data are challenging to interpret both physically, right, and statistically, meaning that different types of proxies are able to capture temperature or precipitation in different ways. And these are subjects in their own right, and certainly I'll be speaking about them, but I'm not a qualified dendrochronologist, right? So to be able to say too much, but I've been able to learn from some of these scientists during the course of these endeavors. So reconstructing past climates and estimating missing data in climate fields and assessing the uncertainty, it becomes essentially I would say, an important statistical problem. Why is it statistical will become pretty apparent very soon, right? And the need for statistical methods for analyzing how to use these paleoclimate proxies to try and infer or hindcast or project back temperatures in the past is important. Now, you may wonder whether, well, I'm not the only one who thinks statistical methods could be important here. Right? Here is a quote from a parliamentary investigation commissioned by Her Majesty's government about a few years ago, right, on the report. It was a report of the international panel set up because of the ClimateGate scandal at Crewe. So he says here, we cannot help remarking that research in an area that depends so heavily, right, on statistical methods have not been carried out in close collaborations with professional statisticians. So there's general consensus, even at very high levels, that these are essentially statistical problems and important for statistical mathematicians to be involved in it. Right? So I'll go back to that was this comment here. But what do I mean by proxy data? Well, proxy data means many things. Here are examples and nice pictures that one of my colleagues allowed me, was kind enough to send to me, was ice cores. Right? So what an ice core does is oxygen isotopes measure, right, in successive years of snowfall, right? One can measure how, roughly speaking, what the temperature was just from the an isotope analysis. Same with corals, right? that corals, during using an isotope analysis, one could get an idea of what the temperature was. Speleotherms and tree rings and sediment cores. So these are what I meant by natural thermometers. So we don't have real thermometers, we have nature's thermometers, which could potentially help us understand this. So I really wanted to try and understand this. As a mathematical scientist, it was difficult for me to see what was going on. So I tried my hand, tried to try and dig a tree or dig into a tree, and it was way too difficult for me. So, so these, well, you know, Kevin Achuketis from Lamont was helping me, was training us, and I realized mathematical sciences was significantly easier. So the instrumental period, which I call the last 150 years, roughly speaking, from 1850 onwards, right? That's where most of thermometer records are available. Proxy data decreases sharply with time. This is from the Michael Mann's 08 database, right? Here is where the green is tree ring data. As you can see, speleotherms is pink, and corals near the Great Barrier Reef, right? And some in the Pacific and so forth. And this is the spatial distribution. And the first thing that one should notice here is that these proxy records are not available in many parts of the ocean, right? So therefore, understanding what temperature was going back farther is even more difficult. And as you can see, coverage is mainly in North America and in Europe, and tree rings somewhat in New Zealand, a little bit in South Africa and South America. So some of these proxies are very unique to special locations. Right?
Is it because they have not been explored, or because of the nature?
Mostly the nature. So for example, so some of these trees would not grow in, for example, in the Democratic Republic of Congo. For example, these particular type of...
the US so covered with those natural thermometers?
The two reasons I would say, some of the late redwood trees, some of the kind of trees that are used are available in temperate zones, right? And less so in equatorial zones. However, there's of course more effort has been made by US and European scientists to first target proxies which are in close proximity. But of course there are some, for example, corals, they're mainly found over here near Perth and near Cairns, the Great Barrier Reef, and so forth. So there is some location-specific reason, and there are also reasons related to the country at hand. Right?
I like to say that it's sort of apples and oranges and bananas. There are ice cores in high latitudes, trees in temperate latitudes, and corals in low latitudes.
So it goes back to exactly what she said, which is that it is...
I'm just trying to make it more colorful.
Yeah, it's proxy specific, because of course I don't suspect that we'll be able to get ice cores in Mexico as much as we would like snow sometimes. So you'd get them in Iceland. Right? And I can see a few in Antarctica too, the blue, right? And corals near where oceans are. So I wouldn't expect to see a coral in the middle of the land. So yeah, it is.
So there is a public database. I mean, you mentioned just Man 08, but there's something called NCDC, the National Center of National Climate Data Center,
right,
where you can just get these for free and
right,
play with them. And it's, I think, the most common. And then there's some of Lamont.
Right.
In principle, if somebody wants to play, you go to
Right.
NCDC.
Right. And Michael Mann's data set also is freely available. Right? But the main point is the spatial coverage is, as you can see, is not very good. And this is time going back. The different proxies, green is tree rings, 2000 all the way, I don't know whether you can see 1000 here. So by the time I get from 2000, the number of proxies decreases from about 1000 to barely 100. So it decreases. What I meant by decreases, both spatially and temporally, it means that if you want to reconstruct or understand what climates were before 1,000 years ago, it becomes increasingly difficult because of this problem, right? And here are the spatial coverage again. You know, by 1850, there are 15 records all over the globe. And I wouldn't say that's encouraging either. I mean, it's not, you will see that these proxies, right, some of them carry weak signals, so just let us not be fooled by the 1300. And then when you go back 250, look at a sudden decrease, right? Fivefold more than that by the time you get to 1500, by 1000 to 54. Another fivefold, and look at this, by 500 is 28. So it decreases very rapidly in time and is skewed towards land areas. By the time we get to 5080s, we mainly see a lot of speleothems, right? So what is our goal here? Our goal is to reconstruct temperature from proxy records. In other words, these tree rings, these ice cores, these lake sediments, and so forth. Now, if we want to reconstruct it over the entire globe, let's say on a 5 degrees by 5 degrees, or on a grid on the Earth, the number of points that you have could be, of the order of 2,000. It could be quite huge, right? And also, usually the number of sample points we have, temperature data, in the last 150 years, is only when we have instrumental data. So only for the last 150 years do we have temperature data. And beyond that, we'd have to estimate somewhat for 2,000 points, right, these temperatures going back in time. It's quite a challenging problem, right? And it's difficult to apply standard statistical methods. Right? If anyone in the audience is a statistician, I'd be very curious to hear how you would tackle this problem, right? So usually there's a multivariate model that is a very basic general model that one can design or set up for this, where you think of each year's, right, data as temperature that you get at different locations, and proxies that you have observed at different locations during the instrumental period. Because if you go back, right, this is the instrumental period. If you go back before the instrumental period, temperature is missing, but we have proxies only. And these proxies, right, here is, in some sense, I am representing the data set in a matrix, right? Here is time going this way, and location, so different temperature recordings or records or proxy records this way over time. Now, proxies are available for during the entire time period, but they don't go all the way back. Not every proxy doesn't go back. Some of them go back up to here, some of them go back. So I don't want you to think that we have full data in these blocks of the matrix. Certainly we don't have data here, right? And often what's assumed is that every year we have data that is independently and identically distributed over time, which is not true, because there could be temporal autocorrelations as climate changes, right? And the distribution could also change. It does not have to be identically distributed, right? So this is a very basic model that has been set up, not by me, but by others. And it forms the basis of an analysis. So what are we trying to do here? Well, the ingredients is that we have what they refer to as a network of proxy records going back in time and in space, a network of temperature records, also instrumental records. Our first goal is to find the relationship between temperature and the proxies. How good are these proxies in calculating or determining temperature, in estimating temperature? Because if they're very good, if we know how to go from one to the other, then we can use that, right? If we know the relationship between temperature and proxies, we can use a relationship to go from proxies to temperature. And that concept is referred to as hindcast. So the first thing that we want to do is to try and find the relationship between temperatures and proxies during the instrumental period, where we have both. So what is the relationship between these two quantities? Now, if I know what the relationship between these two quantities is, I can then use only the relationship during the period where I have only one of those quantities and go back. Simple as that. So those are the two goals that I have. And the third goal is, once I go back in time, I have to also acknowledge the fact that I have done some kind of estimation of the relationship. So there's uncertainty that's associated with this. I need to quantify it. How reliable are my hindcasts? If I say, oh, it's based on my projection, temperature has increased by so much, right, during this current period. Well, how confident am I of that? Because there is a statistical procedure that is involved in these relationship finding the relationship. So therefore, I need to quantify the uncertainty that's associated with it. So this is the main goal of what climate field reconstructions are, or CFR is. Right? Sometimes I shall refer to it as CFR. Okay, so what are the challenges that one faces while trying to undertake these three goals? There are several challenges, right? The first question is, well, if I'm trying to find the relationship between temperature and proxies, how do I find this? Do I do a regression? What kind of curve fitting should I do? Right? That's the first question. Also, as temperature moves in time, this assumption that temperature is independently distributed over time is wrong. There's autocorrelation or serial correlation over time, or temporal correlation, that produces or lead to all kinds of complexities. And there's errors, measurement errors, the way corals are measured, the way tree rings are measured. There are lots of measurement errors that one could get. And also the high dimensionality of the predictors. Sometimes we have 1,300 predictors, 1,300 proxies for 150 years of data. How do we deal with that, right? Which ones are important, right? And then, of course, the spatial modeling part. If I want to do a reconstruction over the entire globe, it becomes much more tricky because I need a model, right, where I say, in the absence of a lot of data going back in time, I need a way to relate different points in space. So we need to do spatial modeling. And there's missing data. And of course, how does one do uncertainty quantifications? And even if we decide on a statistical method, it's not so clear whether frequentist methods or Bayesian methods are better. So there's always these kinds of questions that one has to contend with. So it does become a seriously difficult problem for many of us anyway. So with that introduction at hand, I'll take you through two types of reconstructions, two broad classes of reconstructions over this series of lectures. The first one is to reconstruct the Northern Hemisphere. So what I call a global reconstruction. So I don't want to focus on regions or special areas of interest, right, over the entire globe or the Northern Hemisphere, much more of a global reconstruction. Okay, so that allows me not to model spatial dependency because I only care about one time series. How was the temperature in the Northern Hemisphere going back in time? So just one thing. Not how was the temperature going back in time for every 5x5 grid point on the globe, which is an entire ensemble or entire ensemble of time series in space and in time. So the second part is when I care about spatial or local reconstruction. These are considerably more difficult because you may want to see if the poles have warmed differentially compared to the equatorial Pacific. Have the poles warmed? Is it more now than it was before, right? Before the instrumental period compared to the Pacific? And that's an important question. Where has the warming in let's say, Southern Africa, is it more exacerbated or is it more accentuated now than compared to other places on the globe? So this could be an important question, and it is, and many geoscientists like Arrigo really care about this. And however, it's much more challenging because you need a model. You're asking for much more, not just on just one time series going back in time. So I'll focus on this first, and then I'll focus on the spatial local reconstruction, which is a much more challenging task. Okay. There are various methods that have been proposed to do Northern Hemispheric reconstructions, right? And I say there is this approach that has been dubbed as the hockey stick approach, right? And it's been proposed by many others, as I had said, Manitoul and many others, who have looked at a way to do reconstructions of past climates. And that's, as you will see, there's a lot of regression that's involved. And then thereafter, in recent years, there's been a lot of effort from the statistics community to try and bring uncertainty quantification to these Northern Hemispheric reconstructions, because that's a very important problem. When reconstructions are done, right, what are the error bands associated with the reconstructions? And there's been a lot of work on this and contributions from the National Center for Atmospheric Research, that group IMAGE, and I'll talk about that. And the third part I'll talk about is how do we do robust reconstructions? These reconstructions tend to be quite sensitive to the paleoproxies. We don't want to be at the mercy of a tree being on the different side of a mountain. So how can we do robust reconstructions which are more free of the kind of assumptions, Gaussianity, the type of assumptions that are traditionally made. And we've done some work on that recently in a paper, and I'll talk about that. Right? So that's the main body of work that from a statistical paleoclimate reconstruction point of view that I'll talk about, and I'll reference many of the papers, but in broad strokes I'll give an idea of what's going on. And local reconstructions, well, this is a much more challenging area, and one of the first works that was proposed was the so-called REG-EM framework of Schneider, which is able to take missing values into account and so forth, and hierarchical Bayesian modeling by Tingley and Hybers and ourselves, right, in 2012, and then recently sparse covariance modeling by ourselves in how to do a spatial modeling and still be able to reconstruct climates in the entire globe. So these are the topics that I'll talk about. Today, I'll mainly talk about northern hemispheric reconstructions, right? Okay. So the hockey stick and the associated methodologies, right? I'm sure many of you have heard of the hockey stick, and quite a few, even before the 1998 papers, have looked at the, trying to reconstruct climates of the past, especially northern hemispheres. These are only Lutterberg or Rutherford, Cook, Mann, Bradley and Jones, Crowe and Lowery, Arrigo, so many people. So I don't want to go through the entire literature review except to give you a broad overview of what's really going on, right? And it's also quite a topic that is seemed as very interesting and has caused perhaps some difficulties for some of the researchers. So how do we think about this? What is our first goal? Well, we want to find a relationship between proxies and temperature. The first thing that if you were to ask a statistician, how does one do it? Whether he or she is an applied statistician or a theoretical statistician, the first thing to do is to do a regression, a very basic regression, right? So a linear model where temperature is written as proxies times a vector of coefficient plus error, right? In a more familiar notation, right? Here is temperature at time t is a function, a linear function, right, of the proxies plus error, and the errors have some standard assumptions, right? Now we've all seen this very basic classical ordinary least squares regression, right? And one learns it in very basic classes in statistics. So now let's look at the kind of analysis that's been done as a part of the hockey stick type of approach. So here, let me look at instrumental data from 1902 to 1980 in this case, from the Mann database. And I also look, so that's my instrumental data. They can be integrated to form one northern hemispheric temperature data, which is just one time series only for the northern hemisphere. And we have proxy records going back, about 70 proxies, right, going back up to 1400. You can have more or fewer depending on how far you want to go back, right? This is a high dimensional system. Now, why do I say it's a high dimensional system? Because you have roughly 80 years of data points, right? 80 years of, like 1900 to 1980. And you have 70 proxies. So you have 70 predictors, but you have 80 data points. Your sample size is 80. So it's a high dimensional system because n is of the same order as p. The sample size and the dimension are of the same order. So if you try and do regression, standard regression is very unstable here, right? So how do we overcome this? Of course, the first step is to do a standard regression, right? If you had a few predictors, 4 or 5 predictors and 80 time points, it would be much easier because the standard regression would be more stable, hopefully. So in this case, we have a problem. Well, how the methodology got around this is interesting. This is the proxy location that I was referring to earlier on here, the proxy locations. And here's the tree ring data for the first 14 data. As you can see, I'm just plotting the first 4 tree ring time series. So I have 70 of these. I'm plotting them. And I want to combine these to see how it affects the global temperature anomalies in the northern hemispheres. Can those 3 rings, are they able to reproduce this time series, which is, as you can see, from 1850 to 2000. I'm going to fit it from 1900 to 2000, but you can do that over here. Right? So are they able to mimic what's going on, the different proxies? And when we try and do that, as I said, we have a high... Oh, this is just a smoothly moving average.
In the previous.
Here, yeah, so we had tree ring data from 1400 to 2000. So some moving average was used, some filter was used to smooth it.
They're just individual haircuts.
Yeah, the individual.
It looks like there has been something done to them. They look too smooth.
And also they are constant.
Yes.
Is that the number of?
Yeah, remember, this is from 1400. If you care about 1850, look at this. Yes. So if you care about the current period from 1950 onwards, it's in a very specific narrow region of this curve. These have been smoothed out just for illustrative purposes, for illustration purposes, right? Even here, just a moving average, just to show you the actual temperature points are these circles, right? It's a standard smoother. Now, a question to ask is, well, how do we, essentially when I try and fit this relationship, can these, there are 70 proxies, I only show you 14. How can these be combined to be able to fit this? So it's a linear regression, but we have too many predictors. Which ones are important? Right? And how the methodology gets around it is through principal component regression. So this is also a methodology that has become quite standard. So the idea is to take the proxies and reduce them to a few. Now, how do we do that? Right? So many of you may have known this by different terminologies, empirical orthogonal function analysis, or Cajun-Liouville expansions, or quite a few different words, or orthogonal expansions. The idea is to apply principal components to proxy data. So if you take 70 proxies, you can reduce them to a few, depending on which explain most of the variation in the data, right? And those principal components are now orthogonal. So they're not unstable upon, right? Inversion, for example. So we obtain 70 pieces of length corresponding to the period, but I only want to use the first few in the principal component analysis. So I define the kth principal component, right? You have 1, 2 as UKT. It's also a time series. I've replaced my 70 proxy time series by another 70, which has a certain property. Just think of it that way, which allows me to only consider a few. So if you're not familiar with this, I have 70 proxy records and one response variable, which is my temperature, and 70. I've been trying to reduce the 70 to a few, and this method allows me to do it. So I have 70 of these new time series. I want to just take a few principal components and do the regression. So I undertake a principal component regressions on the new derived variables, right? So I have new time series. It's much easier to do now because I may try k equals 5 or 6 or 7. It's much easier to do, more stable, and I'm able to determine the coefficients. Now, once I do the regression, I could also go back to my original coordinate system if I want, because you can go back between the principal components and the original data. But by looking at only a few principal components, one can do a stable regression. Of course, a question that you want to ask is, how many principal components should I choose? It's not always immediately clear how to do that. So what you could do is you could take just the first principal components, which explain most of the variation in the data. Think of principal components as just a rotation, right, of the coordinate system, which explains the most variation in the data, right? So I could do it with one principal component, or two principal component, or three principal component over the instrumental period and see which fits, which gives me a good fit between, right, in the instrumental period when I try and fit the temperature records to these principal components, because I'm trying to find a relationship, a stable relationship between the two. So I take one, right, I think of it as derived proxies, right? It's a linear combination of the original proxies, that's all it is, with a certain property, right, an optimality property. So I look at one proxy or two proxies or three proxies, and then what I do is, during the instrumental period, I look at the instrumental period and I take one part of it off and try and fit it and see how it predicts in the part that is left out. So it's a way to see how good it is out of sample. So in doing so, we are able to determine the value of k that yields the lowest prediction error out of sample. So you have, let's say, 100 years from, let's say, I don't know, or 80 years from 1900 to 1980. So you can split it into 10 or 8 10-year periods, leave out 1970 to 1980 for the time being, fit the principal component regression from 1900 to 1970. So you have a model which relates the proxies to the temperature. Now go back to the period which you have not used, the period that you have not fitted anything on, the model on. Now try and use the relationship to predict temperature and see how good it is. So that will tell you how many principal components that you need, potentially out of sample. If you use too many principal components, you'll be overfitting, and so therefore your out of sample prediction will be pretty poor. If you use too few, then you'll be underfitting. So out of sample cross-validation, right, is one way to assess how you would tune the fit, right? So, and the output would be the number of principal components you use. And we achieve dimensionality reduction mainly because the number of principal components will be less than 70. Okay. Now the principal component can be used to undertake reconstructions. So in other words, I have now chosen a value of k, so I can say this is what my model is going to be that relates the temperature to the proxies, which is great. Now I'm going to say, let me go back to no longer to the instrumental period or the calibration period, that's where I've done the fitting. Let me go to the historical period and use this relationship to hindcast what temperature was in the past based on this relationship between proxies. Now we have proxies only before 1850. So how do we do this? Well, it's obviously you would just perform the hindcast using the fitted regression. It's essentially an extrapolation, and we call it a hindcast, right? Those are not very different, but I can do it now from 1400 to 1980. Now, once we do that, we're able to reconstruct climates of the past, right? Now, you want to know, well, how good is this? Well, we could, using standard ordinary least squares or some uncertainty quantification approach, we could also get error bands around my prediction error, right, which is uncertainty quantification. So it's 2 standard deviations away from the mean, for example, right? And the standard and straightforward approach without heavy statistical modeling. So what have we really used? We've used linear regressions, we've used principal components, and plus minus 2 times sigma of the estimates, right? So therefore, it's very, very basic statistics, and it's very straightforward and transparent. And here's an example when I use only one principal component. I mean, how many principal components to use is quite tricky. If I use one principal component, as you can see going back, it's not very good. The error is very large. 2 principal components, you can see much more movement in the data, 5, 10. And as you go to 50, you do overfitting, and the fluctuations become larger again. So at 5, we tend to get, for example, for this data set, for 5, we tend to get a reasonable reconstruction, right, going back, and error bands around it. And remember, from 1900 to 1850 onwards is when we have data, and then we reconstruct back all the way to 1950. So as you can see, this is a potentially useful method, and it has been demonstrated to be useful if you want to reconstruct climates of the past, and using very basic statistical techniques. And yes.
That's what the media have referred to.
Yes, yes. But yeah, my question, I mean, I didn't want to be sensational. I just wanted to say they referred to this kind of approach as the hockey stick, right? And I wanted to.
The result, which is called the hockey stick, not the methodology.
No, actually, in many papers, they've referred to as hockey stick methodology. If you look at the Annals of Applied Statistics paper recently, they refer to this as a hockey stick methodology. But that's, again, as I said, let's not focus on the methodology, but more on the science. Here, this was used, this kind of approach was used in the Intergovernmental Panel on Climate Change in 2001 in Assessment Report 3. This methodology is quite a rich methodology because it's quite transparent. At least I use this very basic techniques. And here is what we see in IPCC. And you've seen various versions of this. Yes, go ahead.
They constructed a hockey stick with k equal to 2, which was surprisingly similar. It seems surprisingly similar. So just showing k
right.
5 and 10
Right. So, yeah, so at some point, there's a very good question and a good scientific question, a statistical question is, what value of k should we use? So at some level, it becomes stable. So it's not sensitive to the value of k, and that's very encouraging, because if it's unstable, then one cannot put as much confidence on the reconstruction. Right. So here is what you see, what was in the IPCC report. I want to say this was not in the IPCC report. I'm just using this as a way to show you an example based on the analysis that was done, that the methodology can be used to reconstruct this. So please don't think this is the hockey stick or it's just an application of the methodology. This is what appeared in the IPCC report. Right? And
let me ask you, you know, when I gave a talk that I'll give here, not this today, but in another 2 days, in front of some physicists, and this is not the only time, but you know, Nobel laureate Carlo Rubbia asked, why don't they show us data past 2000? Temperature has not grown for the last 15 years. So I'm actually curious, why does, what's her first name, Tebaldi, actually not do it to 2010, at least?
well, did you want to also answer the question?
That's a gross exaggeration.
I know, but why not put it, you know, why not take care of this question?
I think I'll let them discuss it, but at some point, don't worry, I'll take it back. but okay, so to answer your question, I mean, is it a gross exaggeration? She would say it's a gross exaggeration, and you feel that they have not looked at 2000. Well, there's a very practical reason why this analysis did not include values before 2000, partly because it used data from the MAN 1998 database. So, of course, if the 1998 database will not have values beyond that, one can't, it's like projecting into the future. So it was just an illustration of the methodology rather than the time points in particular. That's a different question. The hiatus question is a different question, the climate change hiatus question. And here, we just wanted to show you what a paleoclimate reconstruction is, not what's happening currently, right? And so the paleo records here in the database do not have the data points from 2000 onwards, but clearly if it was there, it could have been used. And recently that is being done. So yes. But I would think that the questions that have been raised by physicists and also recently in many scientific articles about the hiatus is not as much a paleoclimate reconstruction question going much farther back, but more the comparison between what's happened between 1950 and 1998 and then the last 15 years in the more immediate past rather than going much more farther back. Whereas we are going back, let's say 1,000 or 2,000 years back, which I think is going further back, but there are others who have tried to reconstruct 6,000 years back and 10,000 and even more back. So I just want to place that in context. Okay, so a question that you may be interested in asking is, does the uncertainty quantification about the construction properly take into account all sources of uncertainty? Right? Because we are saying this is what the climates of the past could have been, right? How much trust can we put in these reconstructions? The methodology I just showed you, how accurate are they? Certainly does not incorporate temporal dependency. We assume that the data are distributed independently and identically distributed, right? The data means that we use the standard ordinary least squares methodology that we all often learn, right, in a first course on statistics, how to do ordinary least squares regression. And the errors are independently and identically distributed is an assumption that's often made. And is that true, right? So in the last like 15 minutes, I'll talk about how to do reconstructions with a multi-layered approach to uncertainty quantification, which is statistically more credible. So what has happened is that when this problem became more important, statisticians also got very interested, especially in the last 5-6 years. And I'll talk about an approach that was proposed by Lee et al., who identified 3 important sources of uncertainty, which previous approaches, right, don't always take into account. So there's serial or errors, serial or temporal autocorrelation in the residuals. So that means temperature, as it's progressing along in time, they're not independent. What happens in temperature now does depend on what happened the previous year and so forth. You can demonstrate that in a very basic analysis. So there's temporal dependencies. So there's year-on-year dependencies. And if we don't take that into account, it could in fact affect the uncertainty that we attach to the reconstructions quite adversely. So it could be, so we may be actually saying something that may be wrong or statistically not right in terms of really understanding the uncertainty, right? So the IID assumption may not hold. And also, one of the things that one does is when one does standard paleoclimate reconstruction and hindcast, there's always this problem of overfitting. And this overfitting could affect predictions going back in the past. And there is statistical uncertainty that's associated with that, which I'll go back and explain why. And there's also uncertainty stemming from the calibration approach, because what happens is that when we do a paleoclimate reconstruction, we're fitting a regression. We're getting the regression parameters. Now we assume that those are the truth in some sense, and then we hindcast or we extrapolate. Well, there's uncertainty associated with that. Do we take that into account in a proper way? And there has been efforts to do that even in the previous approach, but a systematic framework has been developed by Lineage-Kahneman. I don't take credit for it, it's not my work. I'm just going to go take you through one of the pieces of work that has been had impact in the field. Right? And the methodology is to keep track of the various sources of uncertainty so that when we say something firm, right, it is statistically credible about these hindcasts. Right? Okay. So what the first thing that the Lineage-Kahneman did was they fitted a regression. Right? They fitted a standard regression just like what you would normally do using ordinary least squares, OLS. Everyone knows how to do that, right? A standard regression. And they looked at the residuals over time after the fit. Now, from basic statistics, we know that the residuals, for the model to hold true, the residuals should be randomly distributed, right? There should not be any autocorrelation. But what they noticed is that there is autocorrelation in the data. So model assumptions are invalidated. So the confidence that you place on the variance or the uncertainty around your parameter estimates is not good. It's not right, because model assumptions have been invalidated. Remember, when I fit a standard linear regression, I assume y is equal to x beta plus epsilon. Epsilon are independently and identically distributed, a very basic assumption. But if we find post-analysis that this is not the case, well, the confidence levels, confidence intervals that we attach to those coefficients are poor, right? And so this is so what they did was to verify this, they worked out something called the autocorrelation function and the partial autocorrelation function of this time series. So if you're not familiar with this, what that does is it looks at the correlation between a time series and its previous point in time. So essentially, you're just looking at, just like basic correlation between two variables, random variables, you look at the correlation between a time series and the same time series one lag behind. And it's clear the autocorrelation function, as your lag goes, is plotted here. I would say, if you haven't seen these before, just that there is temporal autocorrelation at lag 2. That means the residuals not only depend on the previous one, but also on the one before that. At least there is significant statistical evidence to suggest that. So if we don't take that into account, we could run into problems in the uncertainty quantification. So what they do is they said, well, let's try and do this properly, statistically. So let me modify my standard regression approach in a way that is, right, that is fundamentally solid. So let me go back to my linear model with temporal dependencies. I'm back to the regression. I write temperature as a linear function, right? A linear model, beta times pt plus epsilon t. Everything is back. But I model the residuals as an autoregressive process. So what happens here is that the residual is dependent on the previous one and the one before that, plus delta t, which are IID. So the residuals are autocorrelated. Now, if the residuals are autocorrelated here, that means the temperatures will also be correlated, autocorrelated, because this is just a mean function. This is where the only source of randomness comes in. So this is a way of parametrically modeling a time series that's evolving in time, which are not IID, where there is serial autocorrelations, right? It does not have to be an autoregressive process of order 2. It could be an autoregressive process of order q for some q in the natural numbers. right, or autoregressive 3. It just so happens that this plot suggests, the partial autocorrelation function suggests that the lag should be 2, right? So in general, so now how do we fit this model? We no longer have a closed form way of fitting this model. It becomes a slightly more challenging task statistically. How do I estimate? Now I have more parameters. Before I only had beta and sigma squared. Now I have phi 1 and phi 2. So the lag parameters, the autoregressive coefficients, how do I fit those, right? And it's not so clear. So in general, these are not available in closed form. So the standard least squares regression estimate is available in closed form. You don't need to do anything. So there have been approaches using generalized least squares, right, which have been proposed to fit these. And an iterative algorithm to estimate these parameters was proposed. The algorithm goes as follows. The first thing to do is, let me ignore the residuals as if there's no autocorrelations and work out beta. In other words, do the wrong thing, which is ignore the autocorrelation, work out the regression coefficients. After working out the regression coefficients, I subtract from TT minus beta PT to get the residuals. So I could take the residual time series and then fit an autoregressive form to it and to get an estimate of phi 1 and phi 2. So as a starting point, essentially what you're really doing by ignoring the autocorrelation is you start off with values of 0 for phi 1 and phi 2. So you assume they're independently and identically distributed initially. You update beta, then you update phi 1, phi 2, and you go back and forth, right? Now this is an approach to try and estimate this iteratively. Right? Now, of course, a question that you may ask, right, as a mathematician is, well, does this approach for solving this problem, does it converge to the maximum likelihood estimate, right? Does it converge at all to anything, right? And here's the algorithm, and I won't go through it except to say that all I really do is I go back between estimating betas and phis back and forth iteratively. It corresponds to what is called an iterative partial maximization. It's not a coordinate-wise maximization, and there's work that's been done in the optimization community where one can show such iterative partial maximizations algorithms do converge. The rate of convergences are not known, but they do converge. Right? So there is some theoretical guarantees that it will converge. So now, so that's one way of incorporating the temporal autocorrelations. There's a second issue that I identified, or that was identified by Lee and Kahneman, is that overfitting could happen. In other words, when you overfit, this sigma squared could be underestimated because sigma squared reflects the variance of these innovations. This is the residuals, these are the innovations delta t. So when you overfit during the instrumental period, that's where the fitting is happening, there's lots of overfitting. And if you overfit, and when you do a hindcast, it could really affect your hindcast because the fidelity to the data is too strong during the instrumental period or the calibration period. If you fit very closely, right, you could then perform really poorly when you need to do a hindcast, right, because the fidelity to the data, you need the function to be smooth at the same time, have some fidelity but not too strong fidelity, right? So how do we identify, or how do we cope with the overfitting? Well, what Lee and Kahneman do is they said, well, let me see what an estimate of the variance is during the entire instrumental period, and I call it sigma hat squared 1, and then I do the estimate of the same sigma by leaving blocks out to see what the prediction error would be if I were to leave one out and just fit it on the part that's not left out. So I have two estimates of the variance sigma squared, and you can see from that you can estimate a factor of overfitting, and so you can inflate your estimate of your sigma based on this factor to try and get a much better estimate of the sigma, right? So I mean there's lots more detail into this, except all I'm saying is that one can estimate the variance parameter by due to overfitting in an out of sample way, right? Another question that was raised was, well, when we do the hindcast, we use these regression parameters and the phi 1 and phi 2 to do a hindcast because we have a model which we fit during the calibration period, how temperature is related to paleoclimate proxies, right? Once we have that model, we use the parameters from that model to hindcast, to extrapolate back. But these parameters are statistical quantities. They have been estimated from data, so there's randomness associated with them. How do we account for that? Because if we don't, we will make potentially mistakes in terms of not understanding the true uncertainty around our hindcast. In order to do that, what Lineage Kahneman do is they use the bootstrap proposed by Brad Efron as a very standard approach to try and estimate these sampling distributions of these parameter estimates and then do the hindcast. Right? Now, I won't go further into this except to say that this can be applied to a data set, and we applied it to the man data set. Right? Here's a man data set, as you can see again. The proxy is going back rapidly, decreasing rapidly back in time, and the spatial availability of the proxies. Right? And when we do this analysis based on the approach that Lineage Kahneman do, it does get the uncertainty better because it's statistically much more sound. It's able to get at various levels of uncertainty that one has when one does these statistical paleoclimate reconstructions. And when we use 79 proxies which go very far back, we're able to show that large amount of proxies, more than half of them, or 50 to 60 out of the 79, and here they are statistically significant. They are important in terms of being able to in terms of their relationship with temperatures. They are useful, and they're significant at various levels. Here is an autoregressive 2 model for the errors with 3 principal components, right? And at significance values of 10%, 5%, 1%, 0. You will see as much as like 39 out of the 79, so about 50% are significant at the 10% value. So about half are useful, right, at the 10% level. They're statistically significant. That means the relationship between the proxy and the temperature, it is useful in terms of actual prediction. It's not statistically significant. It's not 0, at least statistically, right? And
you might just remember that for non-statisticians, your 10% is 90%.
Yes. Okay. Think of it that way. For a non-statistician, a 10% is 90%, right? If you're a non-statistician.
10% is.
There's a 10%.
Reject the hypothesis.
Yes. So okay. So yes, if you don't know what these p-values are, the significance levels are, under the null hypothesis that there's no relationship, right? This is the significance level at which it would be rejected, right? So I would say that when we get 39 of these, right, are related in the distribution of this beta coefficient, the regression coefficient, which looks at the relationships, fall within the 10, right, percentile, upper 10th percentile, or you would say 90th percentile, beyond the 90th percentile of the distribution of the tails, means that it's not 0. It's actually, these are random quantities, right, under the null hypothesis. These are statistically significantly different from 0. Right? It's very highly unlikely that this could have happened by chance alone. That's what it is saying. Okay, for a non-statistician, I didn't. Thanks, Michael. It's a good way of explaining it. So, but when we do these reconstruction based on this methodology, based on these 79 data points, and we take the uncertainty into account, something not so encouraging happens. So we've done the reconstructions all the way from 1850. This is where we have instrumental records, as you can see, points. And then this is where the hindcasts have been done, all the way up to 1,000. And this is the uncertainty band around that reconstruction. The problem happens is that what do you see? The mean reconstruction, it doesn't pick up the medieval climate anomaly, right? You see the little ice age. It doesn't pick it up. So that's a problem. So a geoscientist looks at it. Sorry, the little ice age, it doesn't pick up the little ice age, like over here, that you see mostly in other reconstructions. So that's a problem. Now what's going on? It's not so clear. Something else it doesn't do is that it's not dynamic in time. Do you see that? It's quite flat. Right? And so it's not dynamic at a sample. The uptick at the beginning of the period that we see in other reconstructions is not reflected here. And the little ice age is not reflected here either. So in terms of the mean reconstruction, there's a problem with this. What's going on? And the uncertainty is also a problem, because if you look at the uncertainty bands, they're very large. Large enough that the uptick that we see here is somewhat within these bands. And that's worrying. And even though statistically one can show that one shouldn't look at it that way, anyone who looks at this curve would say, oh no, look at this uptick is within these bands, there's no warming. So one has to interpret this quite carefully. So, right, and this large uncertainty and
What you call the uptick at the beginning is what's normally people talk about the medieval warm period.
yes.
That's when the Vikings called Greenland green.
Right. So we don't see that here, and we don't see the little ice age. I mean, it's not picking up anything. It's a problem. But that's at the mean level. But also uncertainty is large, and the mean at the end of the period is within these upper 95% prediction intervals. So there is a problem with this. Of course, this is a hemisphere reconstructions. There's no regional spatial reconstructions. So, and it's not particularly robust. So what do we do? So we have to find a different way of tackling this problem. So once we start to take proper uncertainty into account, the kind of confidence band which we thought we had were not true. They become larger. So one has to be careful. So in the next lecture, I'll propose a way that we have designed just very recently, where we attempt to try and bring the uncertainty bands closer, to try and see if we can show that there's what's really happening, to try and get a method which is more reliable or more accurate in terms of the uncertainty, to try and show that it is better. So that's what we'll do and these are acknowledgements to co-authors and others. So I'll stop here and let you ask questions if you want.